Okay. All right, so in this particular problem, we have a golfer that strikes a golf ball at different angles, however, keeping the initial speed the same. So here's the diagram. As you can see, each of these velocity vectors is drawn about the same size, but the only difference here is that the angle is different. Okay, so same initial speed, magnitude VI, but the velocity is different because the angle is, that is being struck is different. All right, and that the bottom graph here gives us the range, aka the horizontal displacement, versus the angle in which the golf ball is being struck. So this graph is super important. Take a second, pause if you need to analyze it. Again, this is the horizontal range, which means how far it travels across in the horizontal direction relative to the angle in which it was launched. So, all right, so keep in mind this is angle versus range. So let's do part A. Part A wants us to find the initial speed, VI. So again, the initial speed is the same every time. The only thing different here is the launch angle. So based on the graph, I can pull this information out. Unless otherwise stated, you can assume everything to be, frictionless or air drag to be ignored. So here, at the peak of the trajectory, here is 47 meters. And that 47 meters represents how far it goes across, the maximum horizontal distance it travels. And that value occurs when the object is being struck at 45 degrees. Okay, so 45 degrees for this particular unit produces the maximum horizontal range. So because I know this is given as 47, and then if I trace all the way down, that angle is right in the middle of 40 and 50, which is 45 degrees. So I can just use the range equation. However, keep in mind that you need to apply physics function correctly and appropriately. You can only use this function here, the range equation here, if and only if delta y is 0, which it is for this case. So if you look at the golfer, the golf ball starts on the ground and then it's being struck, and regardless of the angle, it lands on the same level, which means delta y is 0. So keep that in mind. So here I made a note for you, only if delta y is 0, which it is in this case. Because of that, I can just find VIY by multiplying both sides by g and then dividing both sides by sine 2 theta. Well, what's your range here? Your range is going to be 47 meters, g is negative 9.8, and theta is 45 degrees, because 45 degrees, according to the graph, produces a horizontal range of 47 meters, okay? So if you need to, once again, pause, read the diagram, read the graph, and hopefully keep up here. So to find VI, I'm just going to square root both sides, and then here I'm just going to plug and chug, r being 47 because the graph said so. G is negative 9.8, and then the angle here for sine 2 theta is 45 degrees because the maximum horizontal range occurs at 45 degrees. So just make sure you use the corresponding values here. So at 45 degrees, I go up. The value on my vertical axis, which is my range here, is 47 meters. Okay. All right. So once you do that, simplify the stuff underneath the radical. That'll give you 460.6, and then the square root of that will give you 21.46. So the initial speed, all right, is 21.46, not the velocity. Keep in mind, velocity and speed are different here because the angles are different. The velocities will be different each time, but each time the ball is struck, it leaves the golf club with the same initial speed of 21.46 meters per second. All right, let's move on to part B. Okay, so the answer for A is 21.46, so keep that in mind as we do the rest of the parts. Part B wants you to calculate the time of flight, the total time of flight for 45 degrees. So I think the quickest, easy way to do this is just use your average acceleration function. So acceleration is equal to VF minus VI in the vertical direction divided by time. So to find time, I'm just going to move T up to the top left, at the same time move G to the bottom right. However, what I'm going to do is I'm just going to find the time going up to the peak of the flight, which means VFY is 0. Once I do that, I can just times it by 2 to find the total time of flight, okay? All right, so what is VIY though? Well, to find VIY, all you have to do is really kind of visualize this right triangle. Well, the problem tells you the ball's being struck at some sort of, angle, okay? So that's your initial speed there, VI. Well, knowing VI and knowing theta, I can find VIX and VIY. VIX is simply VI cosine theta. So the adjacent component is simply the hypotenuse times cosine of the angle. Therefore, the vertical component, VIY, is simply the hypotenuse, which is VI here, where I'm tracing back and forth. Once again, VI is your hypotenuse because this is the right triangle, times the sine of theta. This is sine because this is the opposite leg. Well, I need VIY. VIY can be expressed as VI sine theta, so instead of VIY, I can substitute it out. Okay, So VIY is just now VI sine theta. I know VI is 21.46. I know the angle, which is 45 degrees. And then I know G, which is negative 9.8. So I'm just going to plug and chug. Once you do all this kind of stuff in your calculator, the numerator simplifies down to negative 15.17. The denominator is just G, which is just negative 9.8. The negative sign cancels out, so it leaves you with a time of 1.55. However, you don't want to stop here, right? It's important for you to interpret what it is that you just found. I just found the time for it to go from ground to the top of the flight. How do I know that? Because I treat my VFY as 0. And the only spot that VFY is 0 for these types of problems is at the peak of the flight. So that's just halfway. Well, I need to go from top now back down to the ground. So therefore, the total time would be 2 times its value. Okay. So here I highlighted 2 and times that by the time of just halfway. So the total time would be 3.1 seconds. Okay. All right, let's do D. No, excuse me, C. C says calculate the maximum height when it's launched at 75 degrees. So here I'm just going to use my displacement function. However, I'm just going to go ahead and go from top to bottom. Why do I want to go from top to bottom? If I start at the top of the flight for 75 degrees, the VIY is 0, because remember, in these types of problem, VY approaches 0 at the peak. So if I start at the peak, what is my VIY? My VIY is 0 because it has to stop before it turns around in the Y direction. Okay, not the X direction. This is just the Y direction. Well, in order to find out the Y, right, I need to know T. I know G is negative 9.8. Well, how do I find T? So if you kept up with the previous slide, to find T, I can just do VFY minus VIY divided by G. Well, VFY is 0 because I'm going to treat the top of the flight as my reference point. Well, what's VIY? VIY is simply VI sine theta because that's the function I showed you how to do in the previous slide. So if you need to, go back. So here we know everything. VI is 21.46. Well, what's theta? Theta in this case is 75 degrees because part C references the 75 degrees path for the golf ball here. Okay. And G, once again, is given to us as negative 9.8. So once you do all this, the negative sign cancels out, and that will leave you with a time of 2.12 seconds. Well, how do I apply that now? Well, delta Y is just 1/2 GT squared. Once again, you know what G is. The only thing you were missing is T, which I should show you how to do. So once you get to here, just carry the function down. So delta Y is just 1/2 times G, which is negative 9.8 times 2.12 seconds. But don't forget to square that. So once you do all this, you'll get negative 22, right? Well, it's negative 22 meters because I'm using top to bottom. However, well, if you think about it, top to bottom or bottom to top is the same magnitude. So part C asks you to find the height reached when the launch angle is 75. So I'm just going to highlight 22 meters without the negative sign. Why? Because from top to bottom is a positive 22 meters. But height this here is just a scalar. So 22 meters is your answer, okay? All right. So there you go. I just labeled that from ground to the peak of the golf ball when it's being struck at 75 degrees. Above the horizontal axis is 22 meters. All right. Now, if you want to, you can totally use this particular function. So if you've seen my other videos, hmax here when delta Y is 0, yeah, is equal to VI squared sine squared theta over 2G. Okay. Well, what's VI? VI, once again, we already calculated earlier, which is 21.46. Well, sine squared, I just carry that down. 75 degrees here is to the reference angle given part C. And then G, once again, it's just negative 9.8. But you notice here, I only put 9.8 because whether you go up or you come down, the height is the same, right? The distance is the same, you know. So if you threw a ball up 10 meters, coming down is also 10 meters. So if you want, you can put the negative sign in. It doesn't really change anything. But keep in mind, there's a negative sign in front of this VI squared sine squared theta. It's just when you do the hmax equation, it's accepted that the negative signs will naturally cancel out. So we really don't care whether you add the negative sign or not because it naturally will cancel out. Okay. All right. So if you plug and chug all this value in, the value here will be 21.9, as you can see, which is essentially 22 meters, as I previously showed you how to do using the displacement function in the vertical direction. So there's a couple different ways. Pick one that you like. All right. Let's move on. Let's do D. D wants us to find the ratio between the maximum height for 15 degrees versus the maximum height at 75 degrees. So here I'm just going to go ahead and use my hmax function. Why? Because the question here asks for the ratio of hmax. So why not start with the hmax function, right? So I'm just going to apply this a couple of different times here. So here I'm going to split it up. Here on the left side, is for the 15 degrees. Here on the right side is for 75 degrees. Nothing else has changed except for the angle. So here I'm just going to isolate for what are constants. VI square is a constant. 2G is also a constant. So to get VI square and 2G by itself, I will just divide both sides by sine square 15, which goes down to the bottom left there, as you can see. Well, why am I doing that? Because on the right side, I see VI square. I also see a 2G. So all those values are constant for this particular problem. So I'm going to solve for these same constants on the right side by dividing both sides by sine square of 75 degrees. So as you can see, on the right side of the function in each statement, we have VI squared divided by 2G. On the right side, we also have VI squared divided by 2G. So therefore, I can set these two statements equal to each other. So I can say hmax of 15 degrees over hmax of 75 degrees is simply sine square of 15 divided by sine square of 75. Okay, so if you need to do a little algebra there, once you do that, sine square of 15 divided by sine square of 75 on your calculator in degree mode should give you a value of about 0.0718, and that would be your ratio there. Okay. Other than that, let's do E. E uses the same strategy here, but you notice here it's just the ratio here, but the blank is in front of T peak. So how much time does it take to reach the peak at 15 degrees versus how much time does it take to reach the peak at 75 degrees? So let's go ahead and crack it out. But here, because it compares T peak, I'm just going to go ahead and use the function for T for the peak. Why? Because VFY is equal to 0, so I can apply this particular function twice. Okay, but keep in mind, VIY, as I've done a couple of times now, is VI sine of theta. So I can just go ahead and carry this function down on the left side, likewise on the right side. The only thing different here is the numerator, right? Because VIY is VI sine theta, and one is for 15 degrees, one is for 75 degrees. So I'm just going to expand that. So on the left side, instead of VIY, I'm just going to say is VI sine theta. On the right side, it's also the same. It's also VI sine of theta. However, theta on the left side is 15 degrees. Theta on the right side is 75 degrees. So as you can see here, there are constants that you can just go ahead and solve. Or if you want to, you can look at part E, right? It literally says the ratio blank of T peak at 15 equals to T peak of 75. So I know T peak of 15 is this whole entire statement that I'm circling, right? And then I know T peak of 75 is this whole thing that is on the right side because it's set equal to. So I can just say, ready? Blank. Here's the blank where my cursor is for part E. Blank. I carry down with the question mark. Instead of T peak 15, I can substitute out T peak 15 degrees for negative VI sine of 15 over G. So that's where all this stuff is from. Likewise, in the original statement in part E, it says equal, but T peak at 75 degrees. Well, T peak at 75 degrees is simply the same statement except for the angle that's different. So instead of saying T peak of 15, I can set it equal to negative VI sine of 75 over G because that's a true statement. So, well, if you look carefully here, VI and G are on both sides and the negative signs too. So really at the end of the day, to solve for the question mark here, this coefficient, you can just divide both sides by sine of 15 to get it by itself. So the question mark is going to equal to sine of 75 divided by sine of 15 degrees. So if you do it on your calculator, you get a value of 3.73. So that would be the blank here, right? Which makes sense, right? It would take longer to reach the peak at 75 degrees than it is at 15. So the coefficient needs to be bigger than 1. All right, I hope that helps. Stay nerdy. Don't be whack.